Hi, this is Liam Rappolt with the Organic 2 tutorial. I'm going to be talking about the reductions of organic compounds. Now, the first thing we're going to talk about is what compounds get reduced to primary alcohols. So, primary alcohols. Alcohols. General hydrogen. This represents reduction, as we know. So the compounds that are going to end up reacting to form a primary will be the aldehydes, carboxylic acids, and the esters. These will all form primary. And the one that we won't be looking at it directly, but it'll be part of the gist of the tutorial, is ketone getting reduced to form secondary alcohol, because we have these two alkyl groups attached to the alcohol. Now, generally, reduction is just going to occur through maybe a dihydrogen and a metal catalyst. But what we're going to be looking at is a more powerful type of reducing agent known as lithium aluminum hydride, often abbreviated as LAH. And lithium aluminum hydride is so acidic because it's not as nucleophilic, but it is extremely basic, and it can reduce all carbonyl groups as an option, as a resultant, So what I mean by that is that if we throw it in with the carboxylic acid, which is a resonance stabilized conjugate base, so it's a fairly reduction-wise, it's a fairly stable compound. But if we throw it into some LAH with an acid workup afterwards, that should be down there as a subscript, we see that we're going to get a primary alcohol, just like we saw the carboxylic acid, primary alcohol. Looks familiar, right? Mechanistically, this is a fairly straightforward reaction, but we're going to look at it with an ester this time, an even more stable compound. So we'll have, this is our starting ester, and in solution, this is going to just be kind of fairly redundant as a cation. What we're really looking for is the anionic aluminum at the center of 4 hydrogens. We know that this is going to be anionic because there's 1, 2, 3, 4 bonds when it really wants 3. It's in group 13. What's going to happen here, as we know, this is electrophilic as the electron distribution due to the electronegative oxygen. This is going to attack as the nucleophile to the electrophile, bump those oxygens up in an SN2. Looks very simple. What's going to result is this R. This is the carbon in the middle. This is the OR primed. And this is the now negatively charged oxygen with our new nucleophile, which is now our substituent of the carbon. What will happen now, since we have such a good leaving group here, that'll bump down to reform that double bond, and to keep the octet around carbon, this will bump off, giving us back our carbonyl group with another electrophilic carbon, which will react with another equivalent of AlH4 minus. I'm just going to write it like this because we know it actually stands for this now, which will nucleophilically attack, bump those up again. We get another tetrahedral intermediate. These are the tetrahedral intermediates. Tetrahedral. With this, with the negatively charged oxygen, and then just with the acid workup, we have our primary alcohol as our product. Now for LAH, that's an extremely powerful reducing agent, which can be volatile to work with some time. So for a more straightforward and easier mechanism and compound to work with, we can work with sodium borohydride, NaBH4. This is less reactive and less basic than lithium aluminum hydride, which enables us to only reduce more reactive carbonyl groups such as aldehydes and ketones. We look at an ester now, we're going to look at a aldehyde this time. So for an aldehyde, start off with our terminal hydrogen. Same deal with the anionic boron from group 13 and our positively charged sodium floating around in solution. Same SN2 beginning to bump those oxygens up off of that electrophilic carbon, resulting in another tetrahedral intermediate. This will be our R primed with our new H and our negatively charged oxygen. And then following the acid workup, where we just protonate this guy, we'll say that's an acidic solution, it'll result in a primary alcohol.